एडोब में खोलना है क्या? विश्वास नहीं है इस पे। शायद बोल रहे होंगे अनम्यूट करके। तीन के भी दिखा रहा है, बस लगता है पूरा सिस्टम हैंग हो गया भाई।
Shall we start, sir?
इसको बहुत सारे बोल रही है। तीन के भी दिखा रहा है, रन नहीं हो रहा है। डेस्कटॉप पे तो नहीं रखा हूँ। डेस्कटॉप पे क्या करूँ मैं? सर्विस स्टार्ट किसको बोला भाई इसने? रन कैसे करते हैं इसमें? जैसे ही चलाओ फिर रन करके नहीं तो क्या हेलो हाँ बोल दो ना स्टार्ट। Am I audible? Hello.
Yes, sir, audible.
Okay, great. कुछ इंट्रोड्यूस नहीं करेंगे क्या? डायरेक्ट स्टार्ट करना है मैंने। Yeah, Ravi, should I start? Good afternoon, sir.
Good afternoon, all. Respected resource person for the day, respected Principal Dr. Lata Menon ma'am, Vice Principal Professor Vinit Kumar sir, and all the teaching and non-teaching staff. I, Komal Gunjar, Assistant Professor in Department of Chemistry, welcome you all for the third day of FDP entitled Digital Zenith Elevating Security and Nurturing Wellness, jointly organized by Department of Science and Internal Quality Assurance Cell of PLHC College of Arts, Science and Commerce, Rajsthani. Today we have with us Mr. Rohitkumar Upadhyay. He received his BSc degree from NES Ratnam College, Mumbai in 2017 and his MSc degree in mathematics from University of Mumbai in 2019. After MSc, he was an assistant professor for 2.5 years at Kelkar Education Trust, PG Wazir College, Mumbai. He is currently pursuing his PhD at Motilal Nehru National Institute of Technology, Allahabad, Prayagraj, India, starting in 2022. Mr. Upadhyay is also a life member of the Cryptology Research Society of India. His primary research interest lies in secure computation, specifically in fully harmonic inscription and multi-party computation. I, on behalf of PLHC College of Arts, Science and Commerce, Rasani, welcome you, sir, for the session. Sir, now you can proceed with the session.
Hi, thank you for introducing me. Okay, let's start. Can you see the screen?
Yes, sir.
Okay. Hi, good afternoon, everyone. Myself Rohitkumar Upadhyay, and I am going to talk about secure computation. So let us start. So as you can see nowadays, what we are doing, we are having all our data digitally, correct, everywhere. We don't use normal files in folder. Even for payment also, we are not using normal cash. We are doing phone pay, Google Pay and all. So we are going digitally, so we are having so many data. Like if you are individual, there are some datas which you are having: salary, bank detail, Aadhaar card, PAN card, income tax detail, medical data. And okay, slide is not moving or what? Just a second. Okay, so we are having so many data, as I have told you. Uh, if you are individual, these are the data you are having: your fingerprint, your uh, personal details are there, passport number are there, so many details are there, correct. And if you are a profitable organization like Microsoft, IBM, then list of employees and their detail, profit, loss, turnover, salaries. So these are some data which we want to keep safe. If you're educational organization, then again list of employees, number of student and their awards, recognition, publication and dropouts, drug edit. So as you can see, if you are anywhere, you're surrounded by data. So how to keep our data secure, where to keep our data. And out of this list of data, you will see that some of them are private data which you don't want to reveal to anyone. Like age, that is okay, that can be revealed, but you are not going to reveal the balance, how much balance you are having in a account, correct. So there are some data which are very private, which you don't want to make it public. So just, so where to keep our data? So to keep our data, we use cloud like Google Drive, iCloud, Dropbox. There are many cloud service provider where you can keep your data. If you're not keeping in your computer, then you can keep it here in the cloud box. But what about confidentiality? Whether keeping your data in the cloud service provider, whether it is safe or not. Why it is a problem? Because someone, just like for example, whatever you search on Flipkart or something, you used to get the ad of the same thing everywhere, correct. So why it is happening? Because Flipkart is sharing your data to the Google, and then Google is showing the ad related to it. So how can we secure our data? We don't want to share that what we are searching on Flipkart or anywhere, correct. So that is our private detail. So what about confidentiality? Because suppose I am keeping my data to Google Drive, correct, or OneDrive, anywhere I am keeping my data. So what if this Google Drive is uh, sharing my data to some other party or some other organization? So it is called single point of failure. If this is corrupt guy, then I won't able to retrieve my data, or my data will be leaked. My private information which I don't want to share with anyone will be leaked, correct. So the question is how to get secure with this thing. So in the last talk, you know what is secret sharing, correct. So we can use the secret sharing scheme to uh, keep our data securely. For example, suppose I am having my data, I'll create 7 shares of my data and give each share to each one of the cloud service provider. For example, x1 is to this, x2 to this, and like this. And even you can directly use linear secret sharing scheme. That means, yeah, suppose you are having x as a secret, sum of all x1, x2, x3, x7 will be your value of secret, correct. So these are the shares. You nobody see, if you look at Google Drive, it cannot get any information about my secret. It cannot get any information about my secret. Even two three people are there, then it cannot have any information about my secret, correct? Or similarly, you can use the Shamir secret sharing scheme. In the last talk you have seen that if you are having a t degree polynomial, then you will be having uh, you require at least t plus 1 people to retrieve, correct? It will be a t degree polynomial, so there are t plus 1 coefficient in it. So if you are having t plus 1 member, so it will form a t plus 1 degree matrix, and then you can get the information. So I'm not going to talk about secret sharing. You had already listened to a talk yesterday. So we can use secret sharing to secure our data. This is an example. You, whatever secret you are having, you just break into shares and give each share to one of the cloud service provider. In that case, our secret will be not given to anyone. Okay, so in this case data is virtually unleakable and indestructible. Okay. So let me just recall from the first talk, you know about cryptography. What is cryptography? It was secure communication. That means suppose there are two parties, P1 and P2. Mostly I used to call parties. So suppose there are two parties, P1 and P2. So how do they communicate securely? They will encrypt their data by any encryption technique. In the first talk by Sadev sir, you have seen so many crypto system where you can encrypt your data and send it to the other party, and then he will decrypt and get the information. So this is how you can do secure communication. This happens in cryptography, and the goal is privacy, authentication, integrity, and non-repudiation. That is already covered, I think, in the first talk. So I'll go ahead. So next part, as I have shown today, that if I'm having a large amount of data, so instead of keeping it with me, what I'll do, I'll use some cloud like Google Drive or something. I'll put my data directly to the cloud. But there was a problem that what if the cloud is corrupt? So instead of that, I can use secret sharing scheme to share the shares of my secret to some of the, say I'll choose only 5 people of it, and share this share value of my secret to it. Or else I can do one more thing. I can encrypt my data and then give it to any one of the cloud service provider, say Google Drive. I'll encrypt my data. Now in this case, the security lies on the encryption scheme, because if my encryption scheme is secure, then cloud won't be able to know any information, because it has a database which is having encrypted by, correct? So it is ciphertext. So it depends on the security of our encryption scheme. So these are the two steps you can securely keep our data in the storage. Now suppose I have kept all my data in the storage. Now I want to do some computation on my data. What I'll do, I'll either first uh, take out all my data, decrypt everything, and get the plain text and do the computation, correct? Or can I do something like, can I do computation on the encrypted data? So I have shown you two ways. One is by secret sharing, you can keep our data, and one is by encryption, you can keep our data, correct? So there is a question, can we do computation on encrypted data? So whether if you are using a secret sharing scheme or whether you are using any encryption scheme, can we do computation on the ciphertext so that we can find a new ciphertext which is encryption of the computation? So we'll come to it later on. So let me quickly recall what are the things we now know. In cryptography, we take care of protection of data. Look at the first box. There are two parties, so you can communicate but just by encrypting your message and sending to each other, correct? So this is what secure communication is. Second box, look at this blue one. If you are having a large amount of data, you can encrypt the data and send it to the cloud, or you can use a secret sharing. Now the next part is that is modern cryptography. What it deals, can we do computation on the encrypted data? For example, suppose you have kept so many datas in the cloud, and the question is, can we run computation? For examples, can you find a search, can you find the data with the search of anything? Say suppose you are finding all the people who are having 90% above marks. So if you want to search something like this, so you have to decrypt the data and do the search. Question is, can we do computation without doing decryption? Okay, so that comes into secure computation. So this is the branch of secure computation. Now secure computation is the powerful, it can be achieved by two powerful techniques. The first is secure multi-party computation, which is also called as MPC, and second is fully homomorphic encryption, that is FHE. So today's talk I'll be discussing about them. Now next part is, why do we require post quantum security? In the last talk, I think Ramakant sir has already mentioned about why do we need post quantum security. So are traditional crypto systems secure? Because our traditional crypto system lie on integer factorization problem, or discrete logarithm problem, or elliptic curve discrete logarithm problem, correct? So are they secure? Yes, today, but we have to prepare for near future, because in 1994 Peter Shor has given a paper saying that giving a proof that this integer factorization can be broken by a quantum algorithm. So if you are having a quantum computer, it can break the integer factorization problem. That means all the crypto system which are based on integer factorization problem will be not secure. So we all the schemes where all the application of the schemes where we are using RSA or elliptic curve won't be secure enough, correct? So the answer is post quantum cryptography. What is post quantum cryptography? That means a crypto system which are secure against quantum computer, that is called post quantum cryptography. So mostly in cryptography now we are always focusing on the scheme which are secure against quantum computer. Okay, now let us talk about secure multi-party computation. So in MPC, you're having a group of party like this. Say there are n parties. Each of them is having some private data. Say P1 is having their private data x1, P2 is having some private data x2, and like this. And their goal is to find a function f of x1, x2 up to xn without revealing the value of x1. So do you think there are two things? Correctness, parties should obtain the correct output. So they all require this function. And what is the privacy? Each of the party, they don't want to reveal the value of x1. I hope this question is clear. This secure multi-party computation is clear. That means each party, they, without revealing their data, their aim is to find a function on their data, correct? So MPC is easy if we can trust someone, correct? For example, see, if all the parties trust someone, say people X, so everybody trust on X, so everybody give their private data to X, and X can do the computation and give this function f of x1, x2 up to xn, correct? So MPC is easy if we can trust someone. But again the problem is, we cannot trust on someone because he may be corrupt, or he may share our data to other people. So this creates a single point of failure, as I have already told you in the previous slide. So what is the security for MPC? Yeah, as you see that suppose there are n parties and they are sharing the data to a trusted third party, and he will do the computation and give the output. The same security should be given in the real world without revealing anything, any information about the private data. You should able to get the computation. So that should that is the security notion for the multi-party computation. So we have to solve MPC without a trusted party, but it looks impossible, correct? Because you are having data which are private and you have to compute a function on those private data. So how can we do that? Let us see an example. So it is a toy example. Suppose there are, let us take a simple four people. There are four people. Each of them is having their private data x1, x2, x3, x4, and their goal is to compute a function which is say average. So to illustrate, you can understand that each of them is having their private salary as the private data. So P1 is having a salary of x1, P2 is a salary, P2 is having a salary of x2. So they don't want to reveal their salary to anyone else, but their goal is to find the average salary of all four of them. Correct? So can we do something? How to solve this question? Do you see this is a problem of MPC? Because as per the definition we have shown, there are group of party, they want to compute a function on their private data and without revealing their private data, correct? So do you see it is impossible, or do you have any solution? Or else one solution is you ask a third party, say P5, you everybody give their value of xi's to P5, and then P5 can compute the average and reveal it to everyone, correct? So but is there any other way? Suppose parties can interact with each other. So P1 can send email or send message to P2 or P3, anyone. So they are open to that. Okay, let us go ahead. So we will start with first party. His private data is x1. What he does, he add a random value k. So for example, suppose x1 is having a salary of 10,000, so he will add some k. It may be any random value, say 500 or 5,000 or 10,000, something like that, and he will send this value x1 plus k to the next party P2. Now what do you think, after receiving the value of x1 plus k, whether P2 will able to know anything about salary of P1? Whether P2 will have any information about salary of P1? Because as I told you that this k is x1 and k both are secret to this guy, and k is any random value, correct? So it does not have any structure that it will be lying between this and this or something. So after receiving this x1 plus k, it is like one time pad. uh, you are using a key only one time to encrypt. So after receiving this x1 plus k, this P2 won't able to know any information about the salary of x1. So what he will do, he will add his salary in x1 and send it to the next guy, like this. So x1 plus x2 plus k. So P2 will send this value to P3. Now again the same question, P3, can he get any information about salary of P1 or P2 by receiving this value x1 plus x2 plus k? Since k is a random value, so again it will be a it will look like a random number. So he won't able to know any information about the salary of P1 and P2, correct? Similarly, P3 will add his salary and send it to the next guy, and P4 will send it to back to P1. Now P1 had started the system, so he know the value of k. So what he will do, he will subtract the value of k, and from this value he won't able to know any information about other parties, any salary of other parties, correct? So he will subtract the value of k and then announce the result, that is x1 plus x2 plus x3 plus x4. Or you wanted to find average, so you'll divide by 4 and that's it. So do you see that our goal is achieved? We are having the private data x1, x2, x3, x4. We wanted to compute a function on it. The function was finding average salary, and we have done it without any problem, correct? But do you see there are so many assumptions we have taken? The first assumption is the party whom I am trusting, they are not putting any wrong value, correct? So we are trusting that they are putting the correct value of salary. They are not putting, because if they are putting an incorrect salary, so the output will be a problem, so it will be problem for them also. And again, x1 plus k is received to p2. He is adding his x2 in this value. He is not altering anything in the x1 plus k. He is adding his x2. He is not doing anything else to it. So it is a toy example of MPC problem, multi-party computation, correct? Okay. So let us recall each party. P1 first add some key to his salary and send it to P2, and then P2 will add his salary and send it to P3, and similarly all the parties, and in the last P1 will subtract the value key and obtain sum, and then you can announce the result of sum of the salary or average of the salary. Okay. Now, do you see any security concern here? Suppose there are, if there are say P2 and P4, they are friends, they can share their data with each other. Suppose P2 and P4 are coming together, can they find salary of P3? See, P2 is sending this value x1 plus x2 plus k, and P4 is sending this value x1 plus x2 plus x3 plus k. So whenever something like this, for example, there are P8, P9, P10, then P8 and P10 can find the salary of P9. So in between parts, something like that. So how does they do it? For example, see, P2 is having this data x1 plus x2 plus k, and P4 is receiving this data x1 plus x2 plus x3 plus k. So what if they subtract these two value? If they subtract these two value, then they can get the value of x3. So x1 plus x2 plus k will be subtracted and you'll get the value of x3. So if these two party come together, they can get the information of the third party. So this is the security concern. So what else, how can we solve this problem? So instead of P1 is adding some k, you can do one thing. Each of the parties are adding some random value. So he's adding k1 is like this. So this guy is adding some k1. So P2 will add k2 here. So it will be x1 plus x2 plus k1 plus k2. And similarly P3 will be x1 plus x2 plus x3 plus k1 plus k2 plus k3, like that. So once he receive, he will start subtracting. He'll subtract his k1 and send it to P2. P2 will subtract its k2 and send it to next guy, and so on. So at last, so here the circle you have to complete twice. In that case, this problem won't occur. That means if there are two people, then the subtract. And there are some more problem that we are considering the private channel where he's sending the information to others. So we'll leave that part. What are the other issues with this? So there are, okay, so in the last talk you have seen secret sharing scheme. Can we do the same computation by using secret sharing? The goal is you have to compute a function. Each party is having some private data. Can we do something with secret sharing scheme? Yes, we can do it with the Shamir secret sharing scheme. What is Shamir secret sharing scheme? Again, in the last talk you have already seen, we are having a t degree polynomial, then you require at least t plus 1 people to get the secret. So I'll skip this slide. So we have to find some of the private data by using Shamir secret sharing scheme. Let us see, suppose I am having n parties, p1, p2, pi up to pn. Look at this first row. I am having n party. Each of the parties having their secret x1, x2, xi, xn. So this is their secret data. Okay. Now what is Shamir secret sharing scheme? So each of the party will find a polynomial and keep this as a constant, and then evaluate at some evaluation point, and he will create the shares and send it to all the n parties. So he will keep, for example, p1, what he will do, he is having a secret x1, he will create shares of this secret x1. He will create n shares. P1 will keep a share for himself, and then he will give x12 to P2 and x1i to Pi and x1n to Pn. Similarly, P2 is having a secret x2. He will create n shares and he will distribute to all the parties P1, P2 and all the Pn. Similarly, n party is having a secret xn, and he will share the shares to all the n parties. Perfect. Now the question is, suppose I would like to compute 5 into x1 or some constant into x1. So it is very simple. You just, every party is having share for x1, correct? So they can multiply some c to it, whatever c was required, to the shares of x1. So they will get a new share, that is c into x11, c into x12, and like this new share will form of a secret c into x1. So they were having a share for x1. They are getting from by altering the shares, they are getting the shares for secret c into x1. Similarly, suppose you want to add x1 and x2, correct? So what they will do, they will just add the shares of x1 and x2, shares for x1 and x2. Say this x11, x21, like this. So you are having a new set of shares which is for the secret x1 plus x2. Now our goal was to find a secret x1 x2 up to xn, correct? So what they will do, they will add all these shares, x11, x21, all these shares. They will get a new share which is for the secret sum of all xi's. So each of the parties having a share of the secret sum of all xi's, and they will divide by 4, so that will be of average. So they are having a share for average, and by combining they can get the secret, they can get the evaluated point, correct? So here we have achieved MPC goal. That means none of the party, see, P1 have shared his secret value into n parts, correct, n shares. So none of the party won't able to know any information about x1. So that was the Shamir secret sharing scheme. So we had applied Shamir secret sharing scheme and constructed a multi-party computation protocol. Okay, now there are various dimensions to construct a multi-party computation protocol. So we have to take different conditions. For example, whether synchronous, asynchronous. Synchronous is time model. Whether for example, this, the first party is sending a message to second party, then the message received by second party will be forwarded to the next party in the no waiting time. Whereas in non-synchronous, you have to wait. There is no time limit for this. Here x1 plus k, he has to be online all the time. Whenever he receives some information from this, he will send it, add its data to the next party. So that is he has to be online all the time. Whereas in the case of non-synchronous, it is, there is no time bound or something like that. Similarly, simulation phase. Simulation is, as I told you, that in MPC the security is lying that your MPC protocol should give the same security as you are doing the task with a trusted third party. So the proof is with the simulation. So maybe I will skip this slide, for this will be quite advanced topic for the general audience. So I'll go ahead next. There are many real world application of MPC. The first is privacy preserving data mining. As I have already told you that you're having so many data and you want to do some computation on that data, then you can apply multi-party computation protocol. Secure e-auction or private set interaction. Suppose you are having two sets and you want to check whether they are having some common element. So without revealing each of the element of the set, you have to do the computation. So again, then Yao's linear problem. If there are two people, then who is richer without revealing the actual salary, you can find it. This was the first MPC protocol given. So MPC was originated from this problem. Then securely preventing satellite collision. Suppose there are two countries and they are having their satellite, and say third country is launching a new satellite, so it should not collide with any others satellite. The trajectory should not give any collision, so nobody is going to reveal the trajectory of their satellite, how they are performing or something, correct? So without revealing, there should not be a collision. So there is very much real life application of this multi-party computation, and it is widely used. It is, so we'll go ahead to the next part. Okay, so as I told you that secure computation can be done in two ways. First was multi-party computation, and this is the next part, homomorphic encryption. What is homomorphic encryption? We'll see. Suppose here I have some data, so x is the data I am having, and I have to compute some function on this data, say f of x, but my computer is not efficient to do this computation, correct? So what I'll do, I'll outsource, or I'll ask a cloud service provider to do the computation for me. So I'll give my value x and give the function whatever I want to compute. So cloud service provider, or I'll call it as cloud, which is efficient in doing computation, which can do computation, which can do computation, large scale computation, correct? But again the problem is, what if the cloud service provider is a corrupt guy? In this case there is no guarantee of input output privacy. So input privacy means what? Whatever x I am giving, this input will be safe with this guy. He will not send it to someone else, or output whatever f of x I am computing, correct? So is it possible for computationally weak client to not to reveal the data and still outsource the computation? So the answer is encryption, homomorphic encryption. So what is homomorphic encryption? uh, he is going to encrypt his data x, so he is going to give a function f and then encryption of x to the cloud, and then cloud will give him back the encryption of f of x. So cloud has to perform computation on the encrypted value. So with this encrypted value, cloud won't able to know any information about x, correct? And the output whatever will be generated, it will be again encryption of f of x. So from this encryption of f of x, he won't be knowing any information about f of x. So let us recall RSA crypto system. What is RSA crypto system? You are having two primes, and n is p into q, and phi of n is p minus 1 into q minus 1. And I think it was covered with Dev sir, so I'll just quickly go for those who don't know, who are not of mathematical background. You just try to understand like this: if you are having E and D, then product is 1. So how does the encryption work? Whenever you are having a message m, you just find a ciphertext as m raised to e. So this is the ciphertext, and how to decrypt whatever ciphertext you are having. If you raise it to power d, like this, c power d, then this will become m. How is it? If you see the correctness, what is c raised to d? It is m raised to e into d, and I have already told you that e into d is 1. So this will be the message. So it is a simple RS crypto system. Now in 1978, after RSA, there was a paper by Ravesh, Edelman and Daltozhaus, who has proposed a problem that can we do computation on encrypted data. That means doing computation on ciphertext, can we get a new ciphertext which is encryption of some function. For example, let us take RSA. Suppose I am having two message M1 and M2, and I am encrypting the message. So how do we encrypt the message? It is M1 raised to E, and second it will be M2 raised to E. So I'm having two ciphertext. If I multiply both the ciphertext, what I am getting? I am getting a new ciphertext which is encryption of M1 into M2, correct? So suppose I was having two message M1 and M2. I wanted to compute M1 into M2 without revealing the data of M1 and M2. I am able to compute the encryption of M1 and M2. But there is a problem here. Can we do the same thing for addition? If I am having, if I'm adding, if I'm adding two ciphertext, in that case, what happens? You are having encryption of M1 plus encryption of M2. In that case, it won't be of this form, because what do you require? You require that M1 plus M2 raised to E, but that won't be true here. So from 1978, this was the problem, that all the crypto system till 2009, they are partial homomorphic encryption. Partial homomorphic encryption means what? They can perform only one operation. So homomorphic encryption is divided into four parts: partial, somewhat, leveled, and fully homomorphic encryption. So partial is you can perform one operation, somewhat is you can perform both operation but only for limited set of function, and leveled is again you can perform both operation but up to some level of multiplication. So some level will be already defined here. So these two are quite similar. And then fully homomorphic encryption is you can perform computation of any function on encrypted data. That means there is no bound, whereas in the case of somewhat homomorphic there was bound, that you can perform up to only limited set of functions, here up to some level. So what is fully homomorphic encryption? To perform computation on encrypted data for any function. So what is the criteria here? Suppose there is a guy who is having a public key and secret key, and he is having private data x1, x2, xn. This is the private data. The question is, he want to compute this function f of x1, x2, xn. He is not efficient in computing this function. He is inefficient. So what he want to outsource the computation. So instead of directly giving the data to the cloud, he will encrypt the data. So he is encrypting x1, he is encrypting x2 and xn, and sending it to the cloud. Correct. Now we have to give the function also to the cloud. This function may also be encrypted, and the output will be this encrypted value of f of x1, x2, xn. So in this case, look at this, whatever cloud is receiving, it is encrypted value of private data. So it won't able to know any information about the private data, and whatever cloud is giving us, it is again encrypted value of the function. Okay, so this is what fully homomorphic encryption is. It has three main operation. First is encryption, and then doing computation on the encrypted data. Suppose you are having ciphertext c1 and ciphertext c2, then this eval function is giving a new ciphertext, which is encryption of function of m1 and m2. So for you are getting a new ciphertext, you are doing computation on a ciphertext, correct? And the last one is decryption function. This is same as, see, normally any crypto system has this key generation, encryption, decryption, whereas in FHE you are having one more algorithm, that is evaluation algorithm. So there are four variants of FHE scheme after 2009. They are based on different hard problem, and as I told you that we require post quantum security, so all the schemes, all the hard problem, AGCD based FHE, ideal lattices based, and LWE based, NTRU based, all of them are secure against quantum computer. So I am not going to go into the detail due to time constraint. So there are some recent developments. So when this was FHE was first proposed in 2009, after that Professor Lamson has announced that I don't think we'll be seeing using Gentry's solution in our lifetime, because it was very inefficient. It was very slow in computation, and communication was very easy, but the bootstrapping part was very difficult. But after 2001, if you see, in 2001 it requires 1800 seconds. Bootstrapping requires 1800 seconds. Second generation in 2013 it was 172. So every year actually FHE is giving 8 times faster. So in 2001 it just requires 0.5 seconds, so it is more efficient now. Now we can see more practical application of FHE. Next is multi-key FHE. Now this is similar to your multi-party computation. Suppose there are, instead of one party, suppose there are n parties, correct? So, and again the case is whether how to do the computation on the encrypted data. They are inefficient in doing the computation, whereas in MPC they were involving in the computation. They were getting some value, they were performing some addition and subtraction, some function to it, and then they were finding a new shares. Whereas in multi-party multi-key FHE, what we are doing, we are outsourcing the computation part. So here each party is encrypting its data. So say this guy is having public key secret key, its own public key secret key. This is having public key secret key, PK2 secret 2. They will encrypt their data with the public key and they will send it to the cloud. Now what cloud will do? Cloud will perform the computation on the data, the same thing, whatever was happening in the case of FHE, and it will give you a encryption. But this encrypted value will be decrypted only if all the parties are involved here for the encryption. Okay, so this is a concept of multi-key fully homomorphic encryption scheme. Now one can perform two round MPC by multi-key FHE. Now as I told you that in MPC, what was the goal? Goal was to find a function on the encrypted data, correct? There are n parties, they have to find a function on their encrypted data. Same thing can be done with the FHE part. So each of the party will be having their public key, or they can have, there is a concept called multi-party FHE, where they will be having a common public key and each of them will be having a secret key. So they will encrypt their input, their private data with the public key and send it to the cloud, and then cloud will perform the computation and give the result, and then they can perform. Now how can we do it with MPC? Okay, so with multi-key FHE, we can construct a two-round multi-party computation protocol. So what happens here? Each party will first encrypt their data and send it to the cloud. So this is the first round. After that, party doesn't have to be online. Their role is over here. So the next part is cloud is going to perform the computation, and then cloud will output the result. As I have told you, cloud will output the result, and then the same thing will be decrypted. So here the interaction is very less. It is just two round. First round is for encrypting their data, and at last they want to decrypt their data. So we can construct a multi-key FHE scheme by using, it will be a two round multi-key FHE. Now there are various advancement in, hello, is there any problem? Okay, so there are various advancement. The first is you can talk about a batch FHE. What is batch FHE? Suppose you are having some input data, say M1, M2 up to Mn, and you want to compute a function, say f, on each of the data individually. Say for f of M1 you want to compute, then you have to compute f of M2 and so on. So how can you perform batch FHE? Instead of doing the computation n times, instead of encrypting the data n times, what you can do, you can encrypt all the messages M1, M2, Mn into a single ciphertext, and then perform computation on that single ciphertext and get the value of the data. So that is batch FHE. And then you can reduce the bootstrapping time by altering or by using some advanced technique. Then there are some modular switching and scale invariant. And then you can use bit decomposition function for multiple, because see, when you are performing multiplication on ciphertext, it will increase the noise, so it is actually maybe not for the general audience, so I'll skip this part. And multi-key FHE I have already told you, and there is threshold FHE. Threshold FHE, it is similar to this, where there are n parties are there, but all parties are not required to decrypt the function, only t out of them. It is similar to your Shamir secret sharing scheme. You are having n shares, but you require only t number of parties to construct the secret. So it is threshold FHE. You can construct threshold FHE with it. Okay then. Thank you for your attention and time. If you have question, you can ask. If you have any question related to it, you can ask. ज़्यादा जल्दी हो गया क्या? ये
என்னென்ன கம்பி கட்டுற கதையெல்லாம் சொல்றான் பாரு.
इनका इंतजार है भाई प्रेजेंटेशन. सब सो रहे हैं. Ravi, are you there? I am done.
Yes, yes, sir.
Yeah. If you have any question, they can ask or we'll start.
Good afternoon to our principal, Dr. Lata Menon, Vice Principal, Mr. Vinit Kumar sir, respected resource person, and all participants. We know how important it is to ensure confidentiality, security, and authenticity of information in today's digital world. As we came to the end of third day of FDP, titled Digital Zenith Elevating Security and Nurturing Wellness, organized